In this lecture, I want to talk about functional programming, and I'm going to do that by introducing functions over lists. The simplest thing you might ever want to do with a list is sort of go through it and print all the elements out. How do you do that? Well, there's a standard pattern for writing functions over lists. What does it look like? We look at the list the same way that we build a list. How do we build lists? Well, a list is either nil or it's a console. And thus, when we look at a list, we have a case for each of these. So when I write my function, I'm going to take a pointer to a list, and I'm going to look at that pointer. In Scala, we write this with a match to see what kind of thing is pointed to. Is it nil? Or is it a console? If it's nil, I do one thing. If it's a console, I do something else. And a standard pattern in going through all the elements of a list is that when I hit nil, I'll stop. When I hit a console, I will recur on the tail. So this is a very standard pattern. No thought really needed to write it down. It's what the default thing to do on a linked list is. So in this case, what do I have to think about? It's just what I want to do for each particular element. And what I want to do here is print it out. So I can use print or println in Scala to print the element. And on this example list where I have 11, 21, 31, when I call print list, it'll do what I expect. Suppose I want to print these elements in hexadecimal instead of decimal. Well, if I want to do that, then I need to do some formatting. And so I can't leave line 4 exactly as it stands. I need a variant of that. And here's a variant that'll work. I'll just do a format on the element before I print it. And you can see that this indeed does work. I'll get out hexadecimal notation for these elements. I might also have something other than a list of integers. Let's suppose I have a list of lists and I'd like to find out the length of each list or print out the length of each list. Well, I can do that again. It's a really similar structure, but in this case, rather than having a list of integers, I'll have a list of lists. And here on line 4, rather than doing a format, I'll call the length function. So the code here is obviously similar for all three cases, but we can see here two kinds of abstraction that's available to us. So one is that we could abstract away the function that we're performing on line 4. And that would be nice because we could capture this case where we're printing the elements and also the case where we're formatting them. But we also have the type of the list, and it might be nice to abstract over that. So let's first look at just abstracting over the function on line 4. To do that, what I can do is to add a parameter to the function. I'm expecting a function f, and what I'll do is apply that function to the element y. So what is this going to do? It'll apply f to each y in the list as we go down. So y is first bound to 11, then 21, then 31. With this abstraction, it's easy for me to make variations. So with the same FOREACH function, I can also do the formatted printing. So look, nothing changes in FOREACH. The only thing I need to change is which function I'm calling when I invoke FOREACH. So here I'm using the built-in println, and here I'm going to define my own function called printhex, which takes a number and prints it after formatting it. That's great. But in this form, I can't actually use this to deal with a list of lists. So in order to accomplish that, I need to do something called type abstraction. And in Scala, we write this by square bracket x, and we denote the list as being of type x, where x is a variable. And then the function type here, rather than taking integers, are going to take x. Note that the result type of this function is unit. What that means is that it doesn't return an interesting value. In C-like languages, this would correspond to void. In Scala, unit is a type that has one value, and you must always return that value when you have unit. And it's written like this. So this is the unit value. The function that I've taken here in my FOREACH is a function that accepts integers and produces nothing interesting. And that's exactly what println does. In this case, it takes an integer here and returns nothing interesting. When I abstract out here, what I'm going to say is that the function will take an arbitrary type and return nothing interesting. So the important thing here, though, is the connection between the parameter type of the function and the values in the list. So the type of the elements of the list. Because I'm going to invoke this function on each element of the list. And it's important, therefore, that these two types match. In addition to writing the function out like this, I can also write an anonymous version of this function, essentially taking the body here and moving it to where print length is used. This functions that are only used once, it's often too much, giving them too much weight to give them a name. The names often are kind of arbitrary and uninteresting, and so it's often nice to inline those functions. And the way we write this in Scala is simply to essentially copy and paste down here. So this is invoking the FOREACH with an anonymous function. It's useful to note slight difference in the syntax here. In the anonymous function, we have a fat arrow, whereas when we define a method like this, we use the equal sign. So that's sort of the change. I mean, otherwise you can copy this and paste it up here. You're just changing the equal sign to the fat arrow. It's also possible to define anonymous functions at top level. And when you do, those are considered values, not methods. We'll talk more about this difference in another lecture. So what I've got are type and value parameters that I put on my FOREACH function. The type parameter x is written in square brackets, whereas the value parameters here, xs and f, are shown in round brackets. We always put type parameters before the value parameters. F here is a function type. It's a value at function type where the function type is indicated by the fat arrow, so similar to the lambda notation, and the argument of the function is an x and the result is unit. So the way to read this is that f is a function that takes x and gives you back unit. Scala has a built-in FOREACH method, and it's a method of the list class. So you invoke it a little bit differently than you invoke our own FOREACH function that we just defined. So instead of passing the list as the first parameter, you use it on the left-hand side of the dot. Scala can often infer arguments for anonymous functions, and this is quite nice when it works. In some cases, type inference is smarter on methods than it is on functions. And so when I try the same thing with our own FOREACH function that we defined, I actually get an error. Scala is a little upset that I haven't actually put the parameter type on x. The built-in FOREACH also has a special syntax associated with it, which is called a for loop. So I can write this for each x in XS. I'm going to print out the format of x. And what this gets compiled to is simply a call to FOREACH. So the rationale is that this is a little bit easier for programmers to read, and this is nicer for the compiler to actually run. So you can type things in this way, and they will run like this. We'll see that this for syntax is quite interesting. It has a lot of power. The lambda notation is very common in Scala, and writing these kind of things is super duper common. And it's also quite common that when we write our little lambda expressions, that a parameter is used exactly once in the body of the lambda abstraction. And whenever that's the case, when all the parameters are used exactly once, Scala has a really convenient shorthand, which is that you can leave out the parameters and the fat arrow, and instead you just sort of write an expression where you put underscores where the parameters are going to go. And it'll take them from left to right. So the first parameter will be bound here, and the second parameter will be bound here. So this expression is a function of two parameters. And if there's sufficient type information sitting around, you can leave the types off. If I want to define the lambda abstraction version of it, I can write it that way. And here's the underscore version. With for, we have the ability to do imperative loops. So we can declare mutable state, we can go around every element of a list, and we can do something. So here's an imperative version of the sum operation. We're going to set result initially to 0, and then for every element, we'll just add the value of the element into the result. You can even write this in a way that looks really familiar to imperative programmers, because we can write compound expressions. And compound expressions have curly braces, so they look kind of like statements in C or Java. They're not statements, but a compound statement that only, a compound expression that only has one expression in it is really just the same as the expression itself. So these two programs do exactly the same thing. While we can write imperative loops in Scala, we're not going to do it. I'm going to show you a different way of doing this in a subsequent lecture. If you find yourself wanting to print out some information while debugging a recursive function, it's somehow handy to use a compound expression to allow yourself to get some print statements in there. Instead of doing a match directly, put a compound statement where I print before the match and then print after. This is just a function that does nothing. So all it's going to do is run the function and print out this stuff. So on the list 2131, this is the output I get. So it sort of might help you debug what's going on in your recursive functions. Just use compound expressions and print statements. Like most languages you know, Scala has different notions of equality. There's reference equality and value equality. In Scala, we write reference equality with the EQ operator. And in this case, for example, I have a function which takes a list and simply returns the reference that it was given. And you can see that if I have a reference XS and I ask, is that equal to the result of calling this function on XS? The answer is yes. And any two things that are reference equal are also going to be value equals. Value equality checks to see that the value of the pointed to object is the same. It's also possible to create a copy of a list, and I can do that with this simple function right here. So this copy function will go through a list, and if the list is nil, return nil. If it's a console, it will create a new console containing the head element and a pointer to the copy of the tail. And in this case, if we ask, is the list pointer equal or reference equal to its copy, the answer will be no. However, these are value equal. Instead of just creating a copy of a list, a more interesting thing to do is to transform each element of the list as you go forward. And here's a simple example of this, which is going to take a list of integers and produce a new list of strings. So it's sort of a copy, but what I'm going to do here is transform each integer in that original list into a format string in the result list. So going through the list 11, 21, 31 and transforming it will give us the result where we have these hexadecimal strings on the output. How does this work? Well, it works in the standard way we expect a recursive function to work. So we look at the list. If the list is nil, we're returning nil. If it's a console, well, I'm going to return a new console where the head is transformed and the tail is the result of a recursive call to transform. So it's very similar to copy. The difference here is that I'm applying a transform to each element y in the copy. We, of course, could do different transforms. So here's a transform that takes a list of lists and returns a list of their lengths. So if I take this list here, this is a list with 3 elements. The first element is a list of 3. The second is a list of 0. And the third is a list of 2. So if I apply transform to this list, I expect to get the result 3, 0, 2. Let's return to our original transformer and just step through how it executes. If we start with this list 11, 21, 31 nil, when we apply the transform function, we'll immediately pattern match and, of course, choose the cons case. So here y will be bound to 11 and y's will be bound to the remainder of the list. So you can see here when I format 11, I'll get this hex string, and the second half of the resulting console is going to be a result of a recursive call. So recursively, when we transform the remaining list, we will first format the head element of the remaining list, so that's 21, and that gives us this hex string, and apply recursively. So then the third time, we'll apply the formatting string here, getting a third hex string, and finally, when we try to transform nil, we'll immediately bottom out and get nil. Just as we abstracted for the FOREACH function, we can also abstract for this kind of transformation. The resulting function is called map. And what we're going to do first here is to just abstract out the transform that we're performing on each element of the list. So instead of having a specific transformation here, I'm going to add a parameter here. Now, what is that parameter going to do? Well, in this case, it's going to take an integer and turn it into a string. So here I have my function f, which takes integers and produces strings. And then what are we doing overall? Well, we're taking a list of integers into a list of strings. So how do we do this? Well, when we want to invoke it, we are just going to pass a function, and here I'm using the underscore notation. So this is a function which takes one parameter and passes that to the format method of the string class. So formatting a number in hexadecimal. And let me just call this function f for the moment, so you can sort of see how this is going to work. We're going to work through this list by calling map over and over again. So actually this is doing exactly the same thing transform does. It's just doing it through this abstraction f. Here I'm showing the result of the call to f. If I sort of delay that in my printout just to show you what's happening, what you see here is that we're wrapping each argument of the original list in a call to f in the result. As before, we can abstract out the types in addition to the function. And here, the types are actually two different types. So we have the list type x, and then the result type, which is list of y. So what does the transformer function do? Well, it takes elements of type x into elements of type y. Here's such a transformer function. It's going to take a integer and produce a string. And it works just fine. This is very similar to the copy function we had earlier. So let's just go back and compare back and forth between map and copy. So what is map doing? Well, map is going to go into our list and sort of apply f to every element of that list, creating a new copy, if you like, a new list with the resulting elements. Copy does something very similar, except it doesn't transform the elements. In fact, copy is the same as map, where we're passing in the identity function, the function that just returns its argument. So map is related to copy. They're very, very similar in their structure. Map is also related to FOREACH. So what's the difference here between FOREACH and map? In this case, both map and FOREACH have a function parameter. What's the difference? It's that FOREACH is applying the function to y here and throwing the result away. No, the results aren't retained at all as I execute. We just keep the result of the call to the tail. So the resulting value here on FOREACH is actually just going to be the resulting value at nil. Instead, in map, we're retaining all of these intermediate computations and putting them into new concells as we go down the list. Scala has a map function built in, and as with FOREACH, it's a method of the list class. And you can invoke it like this, and it will print out what you expect. This is similar to our map function that we've defined. The difference here is just the syntax in terms of how you invoke it. Also, like FOREACH, Scala provides a for expression, which is a shorthand or a sugar, if you like, for the invocation of the map function. In the case of the map function, we have a for expression that yields something. So the idea here is that when we execute a for expression, we have an iterator, and now for each value of the iterator, we can yield something. If there is no yield in the body of the iterator, then the iterator is assumed to be a for each. If there is a yield, then it'll be some sort of map. So there's lots of things we can do that are interesting with map. So here we can take a list of lists and compute their lengths. Here we can take a list of strings and compute their lengths. There's no end of fun things that you can do with map. So now let's go and look at another function. We've seen FOREACH and map. I want to show you another function called filter. And to introduce filter, I want to go back and recall what copy looked like. So what did copy do? Well, all it does is create a new copy of the list. And you can see here if I have a list of 8 numbers and I create a copy of it, well, the result is just going to have exactly those 8 numbers. What if I don't want all of these values, however? Suppose I only want the ones that are not divisible by 3. How do I do that? Well, we do that using a filter in Scala. So what's a filter? Filter is another functional form. So in this case, we're going to take a predicate and use this predicate to determine which values in the list to retain. So if a value satisfies the predicate, then we'll retain it in the result. But if that does not happen, then we will not retain it. Here I'm showing you a little bit of new syntax for Scala. This is in case expressions, the ability to put a condition. This is a conditional case. And case expressions are evaluated top to bottom. So if case 3 matches, case 4 will not execute. And if instead case 3 does not match, then I know that f of y did not hold, and therefore I don't care about it here. Filters are also built into Scala as a method of the list class. There's also a syntax to use filters in for loops. And the syntax for for loops is similar to the syntax in case statements. What we have here is that for each element z of zs, if the element is not divisible by 3, then I yield that element. This does the same thing as taking a list and filtering it by this predicate. The real power of the for construct becomes clearer when you start doing more complex things. So for example, here, I'm going to filter and then format. I'm going to write 2 function calls using filter and map. But I can do this with a single for loop where I filter and then yield the formatted value. The same technique works with for each. So if I filter and then have a for each, I can also combine that in a single for loop where I write the filter as an if statement and then the body of the for each simply as the body of the for loop. So we've seen for each, map, and filter. Let's look at another function, which again I'll introduce via copy. And I'm going to take a version of copy that's specialized to work on lists of lists. So here's a list of lists, and I have first a list of 3 elements, then a list of 0 elements, then a list of 2 elements. And of course, if I copy, what it's going to do is create a new list referencing those 3 lists. This is a shallow copy that creates 3 new cons cells. It will not recursively copy the sublists. It just copies the top level list and aliases its contents between the original list and the copy. What happens here, though, if we replace this cons operation with Scala's append? So syntactically, all we need to do here is replace the double colon with the triple colon. And what this is going to do is change the resulting type of the list. So instead of returning a list of lists, I will return a list. The resulting function is called flatten. And it's interesting to note that the only difference here is that I've replaced cons with append. And if you look at the execution, indeed, you'll see this borne out as well. So as we execute here, copy is going to create new con cells as it goes down, whereas append is going to append all of these things together. And as a result, in the end, append will give us a list of 5 elements for this example, whereas copy will give us a list of 3 elements. So essentially, flatten is reducing a layer of structure inside of these lists. Just as I can flatten as I copy the elements of a list, I can also flatten as I transform them. To show you this, we're going to look at a version of map that's been specialized to functions that create lists. Here I have such a function. This function takes a number and returns a list of that length. It's using Scala's ranges. This will be the numbers from 1 up to x, and then I'm converting that to a list. So in the case that I provide 3, I'll get the list 1, 2, 3. I'm going to apply the map function then to this example list with 3 elements, 3, 0, and 2. And we'll just take f to be this anonymous function and watch how it executes. So we'll start with the list 302. We'll apply, of course, the function f, that's our anonymous function here, first to 3. That will create the list 1, 2, 3. We then will have a con cell with the recursive call, as we have here. In the recursive call, we'll take y to be 0 and get an empty list. Then in the subsequent call, we'll take y to be 2, and we'll get a list of 2 elements. And finally, when we apply to nil, we'll get nil out. And as a result, we'll have a list with 3 elements, each as shown here. If we replace double colon with triple colon in this function, we end up with something called flat map. And note that here my transform is taking an element into a list, and what I'm getting is a list of lists. That's what map does. What flat map does is it takes a transformer that produces lists and flattens it out as it goes, simply to give you a bigger list. In this case, if we apply flat map, we'll get the same result we had with map. The only difference is that we're going to append all of these lists together rather than consing them all together. And append doesn't create any new con cells. So the resulting list here is going to have these 5 elements in it. We can summarize the difference between map and flat map by looking at what they do when we apply a function f that produces lists. For map, each element in the result will be a list, and the length of the result will be the length of the original argument. For flat map instead, the elements of the result will each be a y, not a list of y, but just a y. And the length of the result is going to be the sum of the lengths of each of the lists that we generate as we apply this transformer. You can see this on the example. We apply the transformer to get the list 1, 2, 3, the list empty, and the list 1, 2. And when we put all those together, we end up with a list whose length is the sum of the lengths of each of the subcalls, or the resulting subcalls. Scala has flat map built in, and it does invoke it using the special for loop syntax. In this case, I have a double iterator, or a nested iterator. So I have a list of lists from which I draw the individual lists. Then nested within that, I'm drawing out the individual elements of those lists. If I then just yield the values, this becomes a flat map with the identity function. So I'm not doing any transform here, I'm just getting the values out. Doing a flat map with the identity function, of course, is just the same as flattening. We can do interesting things here, though. We can do transforms as we perform this. So for example, here, I will take the elements of the list and pair them with the length of the list that they came from. So you can see in this case, 11 gets 3 because it's from a list of length 3, as does 21 and 31. But here, 41 and 51 get 2 because they're from a list of length 2. We don't have to have these kind of dependencies between nested iterators. It's also possible to have these be independent. So here's an example where I have a list 1, 2, 3 and a list AB. And now I'm going to simply say for each x in 1, 2, 3, for each y in AB, yield the pair. In the output, you can see how Scala orders these iterators. We'll draw the elements out of XS in order, and then for each one of those, we draw the elements of YS. So we'll see 11A and 11B before we see 21. If we have independent iterators in a for statement that yields, then the length of the resulting list is going to be the product of the length of each of the individual iterators. This is not true for dependent iterators, but it is true for independent ones. It's worth thinking about the types that are used in a for expression. To do this, let's drill in on one for expression and just look at how Scala handles types in this expression. So here we have 2 lists. One contains integers, the other contains strings, and then my for loop is going to produce pairs. So the types we get in Scala look like this. We have a list of ints, a list of strings, and a list of pairs. How does Scala deduce that this for expression is going to produce a list of pairs? Well, the first thing it does is infer types for the iterator variables, here x and y. So if xs is a list of ints, well then x must be an int, and likewise for y. Given that, Scala then looks for the yield inside of the for expression. If there's a yield, then it will use the yield to give the result type. In this case, the yield is resulting in a pair. Given that x is an int and y is a string, then that pair will have type int string. So whatever type this yield expression has, the entire for will have the type of list of that type, because this is yielding one element. If there's no yield statement in a for expression, what's its type going to be? Unit, because in that case, it's a for each. For loops in Scala are very interesting and very powerful, and it's mentioned in 2 places in the textbook. The brief introduction to for loops you'll find in chapter 7 on built-in control structures. But for a really deep dive in how Scala actually implements for loops, how it translates them into these functions that I provided you in this lecture, you can read For Expressions Revisited. This is only for those of you that are interested, but the subject is fascinating. So that concludes this introduction to functional programming using lists. We've seen for each, map, filter, flatten, and flat map. These functions provide a useful alternative to writing explicit recursive definitions.